Let me give you some brief overview of our AMOS network. I will present some updates, technical updates, and some results from our data, mostly from Hawaii. And naturally, me and my colleagues are working on this joint project with the people who provide logistic on the remote sites in Canary Islands, Chile, and Hawaii. So just briefly, if there is some participants who never heard about the AMOS all-sky Meteor camera, just brief overview. It's an autonomous all-sky system. It's intensified, running in the video mode. It's equipped with the fisheye lens, so that is why we're covering almost all sky. And it has some kind of the closure, which is protecting from the sun, bad weather of the optic inside. The AMOS is equipped with the several sensors, so that is why we can use it in an autonomous mode. At the same time, we can remotely access the camera and set the parameters or force to open the system. So the limiting magnitude in the optical video stream, it's about +5 magnitude. Naturally, for the meteors who are not pointing object but moving along the field of view, it's slightly less. So it's about +4, +3 magnitude, depends on the angular speed. The resolution is 1600 by 1200 pixels in 20 frames per second. In an average, on the very good observatory conditions, we can have about 2000 meteors detected per year. So the network currently consists of 4 locations: Slovakia, Canary Islands, Northern Chile, Atacama, and Hawaii. And there is 10 stations, 5 in Slovakia, and pairs of cameras on Canary Islands, Chile, and Hawaii. So there is years mentioned in the presentation where the actual installation occurred. And now all the system is running smoothly after some technical programs in Canary Islands, which is already fixed. Now there is a cargo flight sending 3 AMOS to Australia with the collaboration of the Curtin University and Desert Fireball Network. So we will use stations on Nullarbor Desert. Each of the 3 AMOS will be equipped with the spectral camera, which is very useful for the possible meteorite recoveries. So there will be some kind of this extension in a close future for South Africa. It means that AMOS will become a real global network soon. I hope so. So the technical parameters for the spectral sub-network of the AMOS, we call it AMOS spec or AMOS spec high resolution. On the left side, you can see some parameters for the spectral camera we use in Slovakia. It's a 100 circular field of view equipped with diffraction rating 1000 gross per millimeter. The sensitivity, we can see even 0 order of faint meteors, but to have this enough signal to noise spectra in the first order, we need at least -2nd magnitude, depends on the angular velocity again, but around -2nd magnitude and brighter events. So we are running this AMOS spec from 2013 when the Regina Rudavska came for a postdoc in Bratislava. And from then, since then, so we have really a few hundreds of the spectra recorded. But the newer spectral system is on the right side, and it's equipped with high resolution camera with smaller field of view. We have about 3 times higher spectral resolution, about 0.5 nanometers per pixel, and slightly sensitive system. We need at least -1.5 magnitude Meteor to be recorded with enough signal to noise ratio. So those higher resolution spectrograph we are running on Canary Islands, Chile, and Hawaii. And as I mentioned, 3 of them are sending now in Australia. So this is just an example of the installation on Halakala, actually on the Airglow building, which is not used anymore. It's next to the decast 4-meter solar telescope you can see on the left, and not very far from the Pan-STARRS telescope and Atlas telescope. So this is just an example of 1 year recording events from Halakala Observatory. It's from 2020 year, and it's a number of detection per night. You can see that there is about few tens or a few hundreds of detection per night. There is also some variation due to the full moon, which is the full moon is depicted at above of the graph, and also there were some gaps during the winter and spring due to the bad weather. But generally on Halakala we have about 80%, 85% of clear nights. You can nicely see the number of the detection which correspond to the meteor showers. Time to time, we have also some false detection like lightings and sprites, but the majority of the almost 30,000 detections are meteors. And just let me briefly introduce some special events we saw from Hawaii last year. This is an example of a very bright fireball simultaneously observed from Halakala and Mauna Kea by AMOS. It was the fireball about -11 magnitude. At the same time, we were able to record the spectra from Spectral AMOS spec from the Mauna Kea. And the orbit and the radiant is very similar to Northern May Ophiuchids meteor shower. What is interesting, the end height was at about 30 kilometers over the sea. So there is a simulation of the fragments trajectories influenced by the winds, similar like Felix presented with Dushan a few minutes earlier. But in this case, it was over the Pacific Ocean, so probably there is some meteorites, if any, at the bottom of the Pacific Ocean. So next, there is a review how many spectra we are able to record from Mauna Kea. Last year we had more than 50 meteor spectra, so it means that 50 meteors with enough brightness in the field of view, which is mostly pointing to the north, were recorded. Naturally, faint meteors of the 0 order is field of view in a field of view of the spectral camera many more times. And this is a special case from the April 2015 this year. It's a bright meteor with higher content of the iron, but also detection of the chromium, magnesium, nickel, calcium, and silicate lines are presented. So this is you can even see the reduced spectra by my colleague Pavel Matlovic, who is responsible for this spectral program, which correspond to the first order of the spectra you can see below. Even very faint line, which is depicted here as an ionized silicon, it's faintly visible here behind sodium line. So So the advantage of the Spectral program is that we are running these Spectral cameras along with the all-sky AMOS cameras, and most of the time we have the simultaneously observed the Meteor or Fireball from both systems. So we have a trajectory and orbital information and spectra at the same time. So this is an advantage running the system simultaneously with the AMOS cameras. And time to time we have some special events recording by AMOS, and this was the re-entry of the artificial space debris body. Actually, it was the Chinese rocket body which re-entry over the Hawaii on October 25 last year. This is a trajectory of one of the last trajectory prediction of this rocket body. You can clearly see that on the left there is a Hawaii Islands, and the prediction was quite precise. And the detection of the re-entries and the fragments over 1 minute from Mauna Kea, you can see here. You can see many of the fragments traveling across the sky from Mauna Kea, and from Halakala it was the event almost in the zenith, so you can even nicely see the separate fragments. Some of them were flickering, and some of them were faint and brighter ones. And this was a record about 1 minute of the path of fragments of this body. So even you can see the animation on the spectral camera. On the left, you might see some very faint spectra of the brightest fragment in the front, and you can even notice the flickering of some of the fragments. Some of them are very stable in the photometry. So now we are working with the students on analyzing the data. Preliminary, the trajectory corresponds to the prediction over the island Maui, where the Halakala Observatory is placed. And we were able to record about 1 minute before actual re-entry over the Hawaii, the bright spot, fragmentation spot, which were about 1,000 kilometers more on the west. So this is just a preliminary trajectory and impacting fragments of different size and masses. And let me finish with one of the very interesting event which was recorded by Subaru Asahi Sky Camera. Shinsuke Aba this morning mentioned the system they are providing from the Subaru telescope site on the Mauna Kea. And this is a camera which is very sensitive, high resolution, which is broadcasting online on YouTube. You can find the videos there. And the camera recorded in July 14 about 12 meteors, faint meteors within 10 seconds. So it's a nice example of the meteor cluster. Probably the fragments were separated just few hours or days before actual entering the atmosphere, and they manifested the similarities on the sky in this field of view. And we were contacted by Shinsuke and found in our records in AMOS some of the brighter ones, members of this cluster. And from two trajectories which were very similar to each other, we can conclude that the original trajectory of this cluster were on a cometary type orbit, and Shinsuke Aba is leading and preparation the paper of our joint data from the Subaru Asahi Meteor camera, from AMOS camera, and also Atlas recorded at least one brighter meteor in larger field of view. So this is just an example that let's say, regular observation or continuation of the observation might bring very interesting events. And my timer already announced me that I used my 15 minutes. And let me conclude with the composite image from the Perseids this year, and unexpected outburst on August 14. At the time over the Halakala Observatory in Hawaii, the radiant of the Perseids were quite low over the horizon, so you can see nice, very long Perseids light streaks, and this is just a good example to expand Meteor coverage as much as possible on global scale to have this kind of the information about unexpected meteor showers. Okay, thank you very much.